Hi everyone, today we're going to explore a graph problem, and the problem is about finding the shortest path in a binary matrix. Now, in this specific case, we are asked to find a clear path in the binary matrix, which is the path from our starting point. We start at 0, 0, to the end point, which is the bottom right point, the n-1 to n-1. Now, a clear path means you also have to travel only through zeros, so we are not allowed to travel through ones. Now, we know that since we're dealing with a matrix, we're going to have to do some kind of iteration to check all these cells and make sure they are valid. Like in this case, for this problem, for them to be valid, they have to be 0. And in case when we don't have a clear path, we cannot go from our starting point, 0, 0, to the destination, n-1, n-1. Then we can just return -1. So essentially, let's say we had 1 here. In this case, we'd never be able to reach our destination, even if we travel through the zeros, since we have 1 here and we cannot cross the path. All right, let's make this one 0, and let's explore some kind of ways we can approach this problem. All right, first of all, we're going to have to do some kind of iteration, right? So from the starting point to the destination, we can use something like, let's say, depth first search, right? Well, if we did depth first search, we would actually be prioritizing depth first instead of exploring multiple pathways. And that would not really be the fastest way to find the shortest path. So exploring many pathways would be much better to actually reach our destination. And actually, if we use something like breadth first search, we'd be guaranteed to find the shortest path, which would be equal to the number of levels that we go down in our breadth first search. So it seems like for this specific problem, when we are dealing with finding the shortest path, breadth first search would be a much better way to iterate our matrix. So let's start planning the solution. So we're going to use some kind of breadth first search. All right. So now we are going to have to consider some edge cases here, because what happens, for example, here, if we have, let's say, if this one is equal to 1. Well, in that case, we're just going to have to return -1 right away, because there is no way we can iterate over this matrix. So if the first cell is equal to 1, we just return -1. And if this cell also happens to be -1, we also just can return -1 right away. So we can check for these edge cases right away, just to make sure that we don't have to iterate the path, the whole matrix. Like, for example, in this case, in the first case, we would actually encounter it in the first iteration of our breadth first search. But here, we'd have to iterate the whole matrix to actually just realize at the end that we cannot reach the destination anyway. So we can start by just checking these two edge cases. So we check when start and end is equal to 1. All right. So now what else? Well, we need to make sure that the cell itself is valid. And for a cell to be valid, we know that it has to be equal to 0, because otherwise, if it's equal to 1, we cannot explore that path. So the cell value itself needs to be equal to 0. So next, all right. So find out what makes a cell valid. Well, it has to be 0. It also needs to be within the boundaries of our matrix when we iterate. And we also need to make sure that when we are checking a certain cell, we have not visited it in the past. Because what happens, for example, let's say we are here in our, all right, let's make this one, let's go back to 0. Let's say we are here. Now we can technically explore this cell too. But if we have reached this cell, it's very likely that we actually came this way. So that's a cell that we have visited in the past. There's no point in exploring that pathway if we came that way already. So for that reason, we eliminate all the cells. We keep track of all the cells that we have visited in the past, and we eliminate them. So basically, they're not going to be considered. All the cells traveled in the past will not be valid. So now what makes it valid? Well, it has to be 0. It has to be within the boundaries of the matrix, and it has to not be visited. All right. So now another thing that we're going to need to consider here is to make sure that we know what makes a neighbor cell. Like, for example, let's say I'm here at this cell, and I want to explore, or hypothetically, just because it's easier to understand, let's say we are at this cell. In this specific case, let's make this one 0. and I want to explore all the neighboring cells. Well, the total number, the max number of the cells that I can explore, it's 8. And we actually, since we know the coordinates of the current cell that we're exploring, we can actually represent all the neighbor cells by subtracting or adding 1 to the column or to the row. Like, for example, let's say we want to explore this cell right here. Well, in that case, we just subtract 1 to the column, and we keep the row the same, because we are essentially staying on the same row, but we are moving 1 to the left in terms of the column. So this one would be represented as 0 for 1 for the row, because the cell is already 1. So we keep the row the same. But now the column is not going to be 1. It will be 1 minus 1, since we're moving to the left, which is 0. So 1 for the row and 0 for the column would end up being this cell. And now we can do the same thing for all other cells. We can essentially use something like an array of pairs, where each pair represent our neighbors. So use a direction array for the pairs that represent the neighbors. All right, so what else? Well, we are going to have to know whether cell we have visited in the past or not, right? So for that, we can actually just use a Boolean array, which will initially be false. The Boolean array will essentially just be a representation of this matrix, where each value is set initially to false, meaning that we have not visited. But then, as we iterate over the matrix, we mark each visited cell to true. All right, next we're going to do a breadth first search. We're going to start with our breadth first search, and for this we're going to use our queue. So essentially here what we're going to do is that we're going to start with the current queue, and then on the next queue we're going to enter the neighbors of the current cell that we are considering. So let's say initially our queue will be equal to 0, and it's going to essentially we are considering this cell here. So the coordinates for the queue, the pair within the queue, will be 0, 0, and we're going to check its neighbors. And here we essentially can check these cells, which are not valid. We check this cell, it's not valid. All right, let's make this one 1. And in this specific case, we end up entering on our next queue only this cell. And then we update the current queue with the next queue. So essentially now this will be our cell, our queue, because we can have multiple cells, which we iterate over on our next iteration. So essentially now we're going to check the neighbors of this cell on our next iteration. And for this cell, the neighbors should be 0 and 0. These are the only 2 valid neighbors. And then on the next iteration, we check the neighbors of this cell and this cell. Now in case of this cell, there are no neighbors. But in case of this cell, we do have neighbors. It's this one. And here, every time that we check the neighbors, before we start even checking for the neighbors, we need to make sure that that cell itself is not the actual destination. Because what happens, for example, if we're here? Well, if we're here, that means the current cell, the row and column, is n-1, n-1, right? So it means we have actually reached the destination. We can just return the number of steps they took for us to reach the destination. And now the number of steps, we know that it's going to be exactly equal to the depth of our breadth first search, essentially the number of times that we are going to iterate and check for neighbors. So that makes it really easy counting the depth and the length of the shortest path. We can essentially just increase the number of steps at each level. All right, so let's start writing the coding practice. Now, as I mentioned earlier, we need to make sure that we enter all the valid neighbors in the next queue, and we update the current queue with the next queue. Now, if we exit because at every time that we are checking the queue, we need to make sure that the queue has some kind of it's at least 1. Because otherwise, it just means that there are no neighbors to be explored. And if the queue is empty, we're just going to exit that loop, our breadth first search, and we're going to return -1. It means that we have something like this case, where we are essentially checking the neighbors of this cell, but there are no neighbors of this cell, which means our next queue would be empty, and for that reason, we would exit our breadth first search. All right. So initially, I'm just going to get the length of the matrix. All right, so I'm going to check for these 2 edge cases. So I want to make sure that the first cell and the last cell, the starting point and the destination, are not equal to 1. The starting point, we know that it's grid 0, 0. And we know that the destination is going to be n-1. Well, in this case, we're just going to return -1. So there is no clear path between our starting point and the destination. All right. So next we can build, let's say, something like a utility function, like a helpful function for us to just check whether a cell is valid or not. And for that, we can just use an arrow function, something like, and in this function as arguments, we're going to get the current pair that we're checking for the specific cell, for the neighbor. And let's call it row and column. And we're going to return true if the row is within the boundaries of our matrix, as mentioned here. So for a cell to be valid, it has to be within the boundaries of our matrix, and it has to be 0. So the row needs to be bigger or equal to 0. The row needs to be smaller than n. And we need to check the same thing for the column. Column, it's going to be smaller than n. All right. We also need to check the value of the cell, which needs to be 0. If we're going to have to consider it, whether we need to iterate, we're going to consider it as an option that we can use to travel in the future to find our destination. We need to make sure that that cell's value is equal to 0. Otherwise, it's just not valid. So the grid value, row and column, needs to be equal to 0. All right. So this will return true only when these conditions are met. So essentially, the cell is within the boundaries of our matrix, and its value is equal to 0. All right, next we can initialize that scene array, which is going to be our array that represents this matrix, and will initially be false for all the cells, because all of them initially have not been visited. Let's call it scene, and then let's populate this with false values. Scene, new array, and so essentially what this is doing is we are creating a two-dimensional representation of this matrix where we are setting each value initially to false. And then once we visit a cell, we mark it as true, meaning that we have visited. And once the cell becomes true, it means we have visited in the past. We do not consider anymore as a member in the next iteration. Like, for example, let's say if we are here. Now, when I consider the neighbors of this one, since I have visited this one in the past, I do not consider that neighbor. I only consider this one because of our scene array. We know that we have entered that value in our scene array. We have visited that cell, essentially. And we said it's the first value. We are guaranteed actually to have a matrix of length at least n in this problem. It's right here. So seeing the first cell, this cell will be initially true. We'll mark it as visited. All right, so now let's build our queue. Initially on the queue, we're going to enter the first pair, the pair for the row and column for this cell, which is our first cell. And the row and column for this cell is 0, 0. All right, so now another thing that we need to make sure we do here is to create a variable that will count the number of the steps they took us to reach our destination. And let's call it steps. And initialize it to 0. All right, so now we check all the neighbors of the current queue. And for that, we create a while loop. We make sure that the current queue is at least 1. The length of the current queue is at least 1. Oh. Now, inside the current queue, we can actually increase the number of steps because we have entered one iteration. Like the moment that we start here, iterating over this cell, we have already done one step. And now when we go to this cell, or the next iteration, that's another step. When we go to this cell, that's another step, and there will be another step. So every time we enter this while loop, we are completing one step. We are increasing the steps by 1. So I'm just going to add 1 to the current step. And I'm also going to get the length of the queue, just to make the iteration later easier, the length of the current queue. And I'm going to create the next queue, which is going to be equal to nothing initially. So essentially what this next queue is going to hold is all the neighbors of the current queue. Our current queue has only 0 of length 1 initially. The neighbors, it's going to be only this one where we check its neighbors. And we're going to enter that one in our current queue. But before we do that, we need to iterate over the current queue because, for example, there can be more than one cell in our current queue. All right, so let's iterate over our queue. All right, so here we need to get the value of we need to get the pair of the current element that we are considering within our queue. And for that, I'm just going to use two variables, row and column again. All right, so before we start checking the neighbors of the current element in the queue, we need to make sure that the current element itself is not the actual destination. Because what happens, for example, if we have reached this cell? Well, in that case, we cannot check any neighbors because we can technically check neighbors, but there's no point on doing that since we have already reached the destination, and that's exactly what we are looking for. So before we check its neighbors, we make sure that the cell itself is not the destination. And for the cell to be the destination, the row has to be n-1 and the column needs to be n-1. So we check if the row -1 and the destination and column n-1. In this case, we are going to return the number of steps. It means we have reached the destination, we just return the steps. All right, so now we are going to check the neighbors. For the neighbors, as I mentioned earlier here, if let's say I'm at this cell, let's just make this 0, and I want to check all the neighbors, I can use a two-dimensional array to check all the neighbors based on the row and column of the current cell. So for that, I can just build an array of pairs for all the neighboring cells. And I'm just going to call this array directions. Now this, all right, let's add one. We know that the max number of pairs that we can check is going to be equal to 8. All right, let's see, this is 8, right. So we're checking all the cells, all the neighbors in relationship to current row and column. So let's say if I want to check this cell, I'm just going to subtract to the current column 1, and I'm going to keep the row the same. So that would be 0. We are going to start with 0. The combination would be 0, 1, 1, 0, 1, 1, -1, -1. And I hope you are following here. So essentially -1, -1. If we were talking about this cell, it would be this neighbor. So essentially we are making our row, we're subtracting 1 to our row, going from 1 to 0. And we are subtracting 1 to our column. So we're going from 1 to 0. We'd be checking that cell by using that pair, referring to that pair. All right, so -1, 1, 1, -1, -1, 0, and 0, -1. Oh, all right, so we need to separate this. So I'll do a quick check to see if I have duplicated values here. All right, it looks good. All right, now next we're going to check whether the neighbors of the current cell, which are, we're going to use this directions array to iterate over it. Like, for example, we can do something like for, let's create two new variables, let's call them dx, dy of directions. And now we're going to update the cells for the neighboring cell. Let's say next row is going to be the current row, the row of our current cell. Let's say for this cell, it's going to be 1, the row, plus the pair in our directions array. So in this case, it would be dx, we are adding the x value in our pair from our directions array. And we are doing the same thing for the column. So for the column, we are adding the y value in our directions array. All right, so now that we have the updated row and column for our neighbors, we will check whether they are valid or if they have been seen in the past. And we said earlier that for them to be valid, they need to meet these conditions. They need to be within the boundaries of our array, and their value needs to be 0. So valid, next row, and next column. And they are not seen in our array. Make sure we use the same updated coordinates. Now, in this case, we are going to mark our current neighbor as seen in our seen array, since we just visited. We set essentially its value to true. This is going to be the current next row and next column. All right. Next, we push that cell, since we already just verified that it's valid, and we can actually use that cell to explore other options in the future, in the next iterations. We push it in our next queue. And then next, we need to make sure we update that queue to the next queue. So essentially, let's say if we were iterating here, these were our queue. Our next queue is going to be this one. And we need to make sure we update the queue, the original queue that we entered, to the next queue. All right. So that in the next iteration, we check the neighbors of this one, and this one, and so on. Now, if you exit this while loop, we are guaranteed to not have found. It means that we reached a point where the next queue was empty. And if we have not reached the destination, we are guaranteed to not have a clear path between the starting point and the destination. So we just return -1. All right, so we're going to do a quick last check. If there's any syntax errors, then we are going to run it. All right, so we check the edge cases. We build this help function here, utility function, to check whether cell is valid. We build our scene array. We populate it with false values. Create our directions array. We initialize the first value of scene. We create our queue, and then we do our breadth first search. All right, so it looks good. I'm going to check these two conditions here. So it looks good. I'm going to start running it. And all right, since here we have, in this case, the answer should be 4. The shortest path would be this here, 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 here. All right, so I'm getting an error. Let's see, next column. This is at 98. All right, there's an extra parenthesis here. Oh, all right, yeah. And this was in the wrong place, right? Well, let's just see one more time. All right, so it's returning -1. The answer in this case should be 4. Let's do one more time. Let's check our steps. Oh, here we actually can just check. All right, so because that is not a array itself, we can just check the pairs right away. All right, let's do one more. Let's run it one more time. All right, 4. All right, so let's try and test these edge cases here. Let's make our first value 1. In this case, the answer should be -1. right, -1. Let's try another case. Let's make this one 0, and let's check. Let's make this one 1. The answer should be also -1. All right, -1. All right, so now let's make this one 0, and let's make this one 0. The answer should be 3. So we can go from here to here to here. That would be our shortest path. All right, 3. All right, so in terms of time and space complexity, now each cell, using this solution, or breadth first search, we know that each cell is visited and processed at most once, since we are using our scene array to mark all the visited cells as false, as true. So initially we mark everything false, but then as we iterate over the array, the visited cells are marked as true. So we do not consider them in the next iteration when we do our breadth first search. And in terms of space complexity, here it's going to be O(n) squared. In the worst case, like a grid full of zeros, the queue and the scene array might store information that is proportional to the number of cells. So now, in terms of optimizations, there are some things that we can potentially do. Like, for example, this condition here, where a cell is where we check whether a cell is valid, we can actually just copy this whole line here and check it right here. But I think that would make the code a little bit less polished. And I think this would be a much more cleaner way of actually writing it. It's much more readable. And another trick that we can use is that we can actually not, if we were allowed to modify the original array, which is not user recommended, we can just mark here. We can mark the next row and column as true in our grid, in our actual grid. We can actually mark it as 1. Sorry, we can just set it to 1, and then our valid row and column will actually eliminate as an option, because we are already checking here if the value of a cell in a grid is equal to 0, and in that case it would be equal to 1. So that would be another trick, but since we are not usually, it's not usually recommended to modify the original input, I think this solution is a little bit, it's definitely better, like for a general purpose solution. All right, so another thing that we can consider is potentially not using a next queue to store all the neighbors, but using the original queue, just removing the last element, the visit, and pushing the new neighbors. But again, it's a little bit less readable, and I think this way is way easier to understand and much cleaner. All right, now this is a very practical, because finding the shortest path, it's a problem that's pretty much in many real-world applications, like for example in Google Maps, or many graphing problems are actually very applicable. But this one is really interesting because it has some restraints, which is very close to the real world, solving problems in real world. So I really hope you enjoyed this problem and had some fun while exploring it. See you in the next one.